4 minutes ago, according to the kind of headline racing across social media, NASA's newest artificial intelligence found something in space that should not exist. The real story is quieter, more complicated, and honestly far more interesting. NASA-backed AI systems are now combing through oceans of telescope data and surfacing patterns that human researchers could easily miss. Some of those patterns are rare enough to look impossible at first glance. But the moment you separate the real data from the wild guesses, you find a revolution that is already changing how we discover planets, strange galaxies, cosmic lenses, and perhaps one day, signs of life. Stick around because I'm about to walk you through what scientists have actually confirmed, what NASA's new generation of AI tools can really do, and why the strangest thing here may not be one mysterious object at all, but the fact that our telescopes have collected more information than humans can realistically inspect on their own. And if you like space stories where we keep the wonder but throw out the exaggeration, subscribe to the channel. That is exactly what we do here. Real discoveries, real numbers, and the mystery that remains after the hype is gone. Let's go back to where the story actually begins. For most of modern astronomy, finding something unusual depended on a human being noticing it. A photographic plate might show a faint smudge, a chart might reveal a periodic dip, a spectrum might contain a line that should not be there. Then an astronomer, sometimes after weeks or months of work, would compare the observation with everything already known and decide whether the signal was interesting. That method worked because the amount of data was still something human teams could, at least in principle, examine. Then digital astronomy exploded. Space telescopes stopped bringing us a handful of precious images and began delivering enormous archives. NASA's Kepler mission watched the brightness of more than 100,000 stars at a time. TESS later spread the search across most of the sky. Hubble built up decades of images. James Webb began producing extraordinarily detailed observations of distant galaxies, stars, planets, and atmospheres. Upcoming observatories are designed to increase that flood even more. The problem is not that astronomers ran out of ideas, they ran out of eyeballs. Imagine placing millions of tiny photographs on the floor of a warehouse and telling a research team that somewhere in that pile are the 5 images that could change a field. Now imagine that new boxes keep arriving every day. That is the basic scale problem. Astronomers can build filters and automatic pipelines, but traditional software is often based on rules chosen in advance. If the signal behaves exactly as expected, those rules work beautifully. If nature produces something unusual, the very thing you are most interested in might be the thing your rules were never designed to recognize. This is where machine learning became so powerful. Instead of telling a computer every possible pattern it should search for, researchers can train a system on large collections of known examples. The software learns which combinations of features tend to belong to real planets, false alarms, galaxies, instrument artifacts, or unusual events. It is not thinking like a human. It is not becoming curious. In simple terms, it is becoming very good at separating patterns. And that distinction matters, because the phrase NASA AI can make this sound like some all-knowing digital astronomer sitting inside a control room and suddenly announcing that physics has broken. That is not what is happening. The real systems are specialized tools. Some classify candidates, some rank anomalies, some identify patterns in images, some help engineers monitor spacecraft. The power comes from speed, consistency, and the ability to examine datasets so large that no person could reasonably inspect them one by one. For years, one of astronomy's biggest examples came from the search for exoplanets, worlds orbiting other stars. The most common technique watches for a transit, the tiny drop in starlight that occurs when a planet crosses in front of its star. If you stood far away and watched our sun, Jupiter would block only about 1% of its light. Earth would block far less. The change can be subtle enough that stellar activity, background stars, binary companions, or detector effects can imitate it. So every promising dip is not automatically a planet. It is a suspect. In 2017, researchers Christopher Chaloux and Andrew Vanderberg used a neural network to search Kepler data and identified Kepler 90I, an 8th planet in a system about 2,500 light-years away. The result, announced by NASA on December 14, 2017, showed that machine learning could recover planetary signals hidden inside data humans had already processed. The discovery made Kepler 90 the first known star, other than the Sun, known at that time to host 8 planets. It did not mean AI had surpassed physics. It meant the same measurements could reveal more when examined in a new way. But that was just the beginning. NASA researchers at Ames Research Center later developed ExoMiner, a deep neural network built specifically to distinguish real exoplanets from false positives. ExoMiner was not simply shown pictures and told to guess. Its design was inspired by the kinds of diagnostic tests human experts use when validating planet candidates. It examined multiple clues in the light curves, compared them with patterns from confirmed planets and known imposters, and produced classifications that researchers could investigate. The pivotal turning point came in 2021, when the ExoMiner team used the system on Kepler candidate data and validated hundreds of new worlds. NASA reported 301 newly validated exoplanets in November of that year, and the research led by Hamed Valizadegan and colleagues was published in the Astrophysical Journal. This matters because validation is not the same as merely spotting a weird dip. The whole point is to test whether an apparently planetary signal is better explained by something else. It had exactly one job: be skeptical at a scale humans could not match. The first major finding is that AI can pull genuine planets from old data that appeared, to human workflows, already thoroughly searched. That is a strange idea when you sit with it. We tend to picture discovery as a telescope turning toward a new patch of sky. But a discovery can also happen while the telescope is gone, the mission is over, and the photons were recorded years ago. Nothing in the universe changes. Our ability to recognize the pattern changes. By January 2026, NASA described a newer system called ExoMiner++, trained using data from both Kepler and TESS. NASA said the ExoMiner family had already been used to validate 370 exoplanets, and the updated model was designed to dig into the far larger and more varied stream of TESS observations. TESS surveys huge areas of the sky, meaning the software has to deal with stars of many types, different observing conditions, and candidate signals that can be far messier than a clean textbook transit. Here is the detail that tends to stop people in their tracks. Every time an AI system learns to recognize what a normal planet signal looks like, it also becomes better positioned to notice when something does not fit. Not impossible in the sense that the laws of nature have failed, but unusual enough that a human team may need to ask a new question. And that brings us to the second discovery. In January 2026, astronomers reported using an AI-assisted approach to examine nearly 100 million small image cutouts from the Hubble Legacy Archive. That number is worth pausing on. 100 million. If you spent just 1 second looking at each cutout without sleeping, eating, or blinking, it would take more than 3 years to finish. A human research team cannot seriously perform that task by eye. A machine can rank the unusual cases and hand people a much smaller set worth investigating. NASA described the work as uncovering hundreds of cosmic anomalies in archived Hubble data. These were not necessarily violations of known physics. The word anomaly in science usually means something that differs from the patterns expected by the model or the majority of the sample. That could mean a rare galaxy shape, a gravitational lens, an odd interaction, a merger, or some other uncommon structure. The AI does not get the final word. It raises its hand and says, essentially, you should look here. That is exactly what this kind of system is able to do. Think about what that changes. In older astronomy, the bottleneck was collecting enough light. Today, for many projects, the bottleneck is attention. We already possess archives containing discoveries nobody has recognized yet. The photons have arrived. The images are stored. The signal may be sitting on a server. What is missing is the act of noticing. If that idea fascinates you, drop a like, because this is one of those changes that sounds technical but completely reshapes how science works. A like helps more people find the video, and more importantly, it tells me you want these deep dives into the real mechanics behind the headlines, rather than just another dramatic claim with no explanation. There is a second layer to this Hubble story that makes it even more important. Anomaly hunting is different from ordinary classification. Classification asks, which known box does this object belong in? Anomaly detection asks, which objects do not fit the boxes very well? The first method organizes the universe. The second method hunts for surprises. And surprises are dangerous territory, scientifically speaking, because they are where excitement and error can look almost identical. An unusual image might be a rare astrophysical event. It might also be a cosmic ray striking the detector, a processing artifact, contamination, a bad pixel, an alignment problem, or a familiar object viewed from an unfamiliar angle. Researchers therefore have to trace the signal back through the instrument, the calibration, the observing history, and independent measurements. This is the part viral posts usually skip. Discovery is not the moment a computer circles something strange. Discovery is the long process of surviving every attempt to explain the signal away. The third finding tends to unsettle people the most, because it changes where we draw the boundary between telescope and scientist. AI is moving closer to the instruments themselves. NASA and other research groups are developing machine learning systems not only to analyze archive data on Earth, but also to support mission operations, spacecraft health monitoring, scheduling, data prioritization, and anomaly detection. A NASA technical report prepared for work connected with the future Habitable Worlds Observatory described possible uses including spacecraft health monitoring, automated scheduling, flexible execution, real-time data evaluation, prioritization, and onboard data compression. In other words, future observatories may increasingly decide which information deserves immediate attention before all of that information is even sent home. That sounds like a minor engineering upgrade. It is not. Spacecraft operate under brutal limits. They have limited power, limited bandwidth, limited time. A telescope can sometimes collect more raw information than it can conveniently transmit. If an onboard system can identify a rare event, prioritize an image, compress unimportant data, or alert operators to unexpected behavior, then the spacecraft becomes more responsive to the universe it is observing. Not conscious, not independent in the science fiction sense, responsive. And then there is the reason this matters so much for future planet searches. NASA is developing the Habitable Worlds Observatory concept with the goal of directly studying potentially Earth-like planets around Sun-like stars. Direct imaging is brutally difficult because a planet can be billions of times fainter than the star beside it. Imagine trying to see a firefly hovering beside a lighthouse from thousands of miles away. Now add telescope vibrations, optical imperfections, stellar activity, detector noise, and light scattered through the instrument. That tiny planetary signal is buried under layers of interference. Machine learning researchers at NASA's Jet Propulsion Laboratory are already studying methods for separating weak exoplanet signals from stellar and instrumental noise in extremely precise measurements. The goal is not to manufacture a planet from noise. It is the opposite. To understand the noise so well that a genuine planetary signal has fewer places to hide. To understand why this matters, you have to understand what astronomers ultimately want from an Earth-like planet. Finding the dot is only step one. The real prize is light from the planet itself, spread into a spectrum. A spectrum is basically light broken into its component colors, and those colors can reveal which molecules are absorbing particular wavelengths. Water vapor, carbon dioxide, methane, oxygen, none of these molecules by itself automatically means life. That is crucial. Oxygen can be produced without biology under some conditions. Methane can come from geological processes. Even combinations of gases have to be interpreted in the context of the star, the planet's temperature, its atmosphere, its history, and possible non-living chemistry. This is exactly where hype becomes dangerous. A machine learning model may identify a spectral pattern worth examining. A statistical analysis may say one atmospheric explanation fits better than another. That is not the same as NASA announcing aliens. It is not even the same as confirming life. Researchers would demand repeated observations, independent analyses, careful modeling, and a serious effort to rule out false positives. Still, the reason scientists are building these tools is extraordinary. We are entering an era when the signal of another world's atmosphere may be so faint and the data around it so complicated that artificial intelligence becomes one of the tools helping us decide where to look more closely. If you want, drop a comment telling me what you find more fascinating. AI uncovering hidden planets and old data, or AI helping future telescopes search atmospheres for subtle chemical patterns. I'm genuinely curious because those are two very different versions of the same revolution. One is archaeology inside our archives, and the other is a new way of exploring places we have never seen directly. Now picture for a moment what this actually feels like from the point of view of the data. A star shines for millions or billions of years. Somewhere around it, perhaps a planet moves through its orbit. Once per orbit, from our particular angle, that planet crosses the face of the star and blocks a tiny fraction of the light. The missing photons travel across hundreds of light years and never arrive at the telescope. What does arrive is collected by a mirror, converted into electrical signals, digitized, transmitted across space, processed on Earth, calibrated, archived, and eventually reduced to a line on a graph. The planet itself is not in the graph. Only its shadow is. Now imagine that graph entering a database with millions of others. Years pass. The telescope moves on. Engineers retire. New missions launch. Then a model, trained on thousands of examples, examines the pattern and assigns it a high probability of being real. A scientist sees the candidate, checks the diagnostics, compares neighboring stars, studies the shape of the transit, searches for alternative explanations, and eventually, a world that had been physically present all along becomes scientifically visible. Nothing was created, something was recognized. That may be the most important idea in this entire story, because when people hear AI detected something impossible in space, they often imagine an object that breaks physics, a structure moving faster than light, a planet older than the universe, an artificial signal, a giant machine, some impossible geometry. Those stories spread because impossible is a powerful word. But in real science, impossible usually means one of three things. The measurement is wrong, the model is incomplete, or the event is rare enough that our intuition was never trained to expect it. All three possibilities are valuable. A bad measurement teaches engineers how an instrument can fail. An incomplete model can open new science. A rare but natural event can reveal a part of the universe we hardly ever get to observe. The job is not to protect the word impossible. The job is to attack the anomaly with every boring explanation available and see what survives. And that is why AI is becoming so useful. It can increase the number of anomalies we find without lowering the scientific standard needed to explain them. There is also a bigger statistical reason this transition is unavoidable. Astronomy is entering the age of surveys. Instead of studying one galaxy, one star, or one planet at a time, modern observatories can map enormous populations. TESS monitors vast numbers of stars. Hubble's archive spans decades. The Nancy Grace Roman Space Telescope is expected to conduct wide-field surveys and discover or characterize enormous numbers of cosmic objects. NASA has specifically pointed to future Roman exoplanet data as an opportunity for tools descended from ExoMiner. The larger the survey, the more likely it becomes that the rarest things are hiding inside it. Suppose an event occurs once in every 10 million objects. A catalog containing 100,000 objects might never see it. A catalog containing 100 million could contain several examples. Suddenly, something that felt impossible becomes a population you can study. This is why the future of AI astronomy is not really about replacing astronomers. It is about expanding the searchable universe. A person is still needed to ask whether a pattern matters. A person is still needed to understand the instrument. A person is still needed to compare physical models, design follow-up observations, challenge assumptions, and decide what evidence would actually confirm a claim. But AI can act like an impossibly patient assistant, checking one light curve after another, one cutout after another, looking for the handful that deserve human attention. And the deeper implication goes beyond planets. The same broad logic applies to gravitational lenses, supernovae, variable stars, asteroid detection, solar activity, galaxy morphology, radio transients, spacecraft telemetry, and any field where rare signals are buried in huge streams of data. Once the number of observations becomes too large for direct human review, some form of automated prioritization is not optional. It becomes part of the scientific instrument. That changes the meaning of a telescope. A telescope used to be a machine that gathered light. Increasingly, it is becoming a system that gathers light, processes information, filters patterns, and helps decide what should be looked at next. And when that happens, the boundary between observation and interpretation starts to move. Not disappear, move. That distinction is important because there are real risks. Machine learning systems can inherit biases from their training data. They can perform poorly when they encounter patterns unlike anything in the examples they learn from. They can become difficult to interpret. A model can be confidently wrong. If researchers only search for the kinds of objects the system already knows, genuinely new phenomena could even be suppressed rather than highlighted. This is why explainability matters so much in scientific AI. Researchers do not merely want a black box that says planet or not planet. They want to know which features drove the decision. They want diagnostic plots. They want uncertainty estimates. They want to be able to challenge the output. ExoMiner was designed with this scientific context in mind. Its architecture incorporated diagnostic concepts used by human experts, and NASA emphasized its role in distinguishing planets from false positives rather than simply generating exciting candidates. The point was credibility at scale. So, what does all of this actually add up to? It adds up to a transformation in how discoveries happen. We began with a dramatic claim. NASA's new AI detected something impossible in space. The confirmed reality is that NASA and NASA-supported researchers are deploying increasingly capable AI and machine learning tools to validate exoplanets, search huge archives, identify rare anomalies, improve mission operations, and prepare for observatories whose data volumes will overwhelm traditional analysis. We have already seen machine learning recover planets from Kepler data. We have seen ExoMiner validate hundreds of worlds. We have seen AI-assisted methods comb through nearly 100 million Hubble image cutouts and flag unusual cosmic objects. We are seeing AI incorporated into the planning for future observatories and into the broader challenge of detecting weak signals buried under stellar and instrumental noise. What we do not have is verified evidence that 4 minutes ago, NASA announced an object that literally violates known physics. And I think the real story is better, because a universe does not need to break the laws of nature to surprise us. It only needs to be larger, older, more varied, and more information-rich than our minds can easily process. Every telescope adds another layer. Every archive grows. Every new algorithm changes which patterns become visible. The uncomfortable possibility is not that AI has already found the impossible. It is that thousands of important discoveries may already be sitting inside data we possess, waiting for the right way of looking. Somewhere in an old light curve, there may be a planet no one noticed. Somewhere in a Hubble image, there may be an unusual gravitational lens or a galaxy caught in a rare phase. Somewhere in future Roman data, there may be an event so uncommon that no astronomer would think to search for it directly. And one day, in the spectrum of a small world around another star, there may be a chemical pattern that forces us to spend years asking the hardest question in astronomy. Could something be alive there? If that day comes, the first alert may not sound like a human shout in a control room. It may begin as a score in a database, a flagged spectrum, a strange residual, or a pattern a machine says does not look like the others. Then humans will do what science has always required. We will doubt it. We will test it. We will try to break it. And if it survives, we will look again. That is the image I want to leave you with. Not a computer declaring that the universe is impossible, but a quiet system scanning the darkness, line after line, pixel after pixel, while somewhere inside that ocean of data, a real signal waits to be recognized. More data is still coming, and the tools searching it are getting better. So subscribe and turn on notifications if you want to follow the discoveries without the exaggeration. Drop a comment with the kind of signal you think would be hardest to believe even after scientists confirmed it. Share this video with someone who sees those "NASA just found the impossible" headlines and wants to know what is actually happening behind them. Thanks for watching, and I will see you in the next.